Welcome back to my tutorial channel, and I found this out when I was noodling around with the Ocean Evaluate while I was doing my other tutorials, and I noticed that you can output volumes, surface, height, velocity, hydrostatic pressure, and I tried to come up with something that would be useful from these volumes. So you've got an object, you want it to float realistically on the water and interact with the waves. This does it really well. No .NET, it's quick, it's tunable, so let's dive in. Right, so I've got your standard setup here. Got a grid, an ocean spectrum, and an ocean evaluate. And first thing I want to do is to set up the ocean evaluate volumes here. Down here, we'll start off with an SDF, and we want to use the grid as a guide to what's going on with the volume. So I'm going to make the grid the same resolution as the volume. So what I'm going to do is I'm going to copy the size of the grid. We want it to be square, so I'll put that in there as well and change it to 30 meters. Do the same thing with the rows, so I'll copy parameter, put that to 60, and I'm going to put a null and I'm just going to load that into there. Just to make it a bit easier to view the water while I'm working on the other thing. Okay, moving back to this. Surface SDF for now, and I want the resolution to be the same as that. So if we just have a quick look at this, there's our SDF. Okay, so it's positive above the water and negative below the water. If I change the range is to -1, no, say -5 to 5, you can see it's a smooth gradation and it's 0 in the middle where the water goes through. So we can tell if a point is above the water or below the water. That's the point of this. Great, delete that for now. So moving over to our pig. I've got an ordinary pig head, scale 2. And I've just filled the gap on the bottom and put the material on those faces so that it doesn't look nasty. And the next thing I'm going to do is convert it to dots, points, which we're going to use to sample the SDF field. Okay, so points from volume. If I go, I'll use a attribute from volume node. And we'll call that attribute surface. Attribute size is 1. And we can see that surface varies from -3 to +1. And if I show that object. If I put that object on, we can see that it's mostly underwater. So we want to start off above the water, so we'll put a transform in there. Transform. Put that 5 up in the air. Good, so we've got a pig, we've got some points, and we can pull an attribute in from the field. So let me just show you the hack that I'm going to use to get this to interact and move around with the field. Okay, so if I make a group of these points, my bounding box, right, just the top view, points, turn the C off for now, and then we move those a little bit. Right, then we use the extract transform it gives us a point which we can then use to copy the original object back onto, which would be that one. So now we can see when we move that small group of points around, causes our object to rotate and move with it. So it kind of averages out the positions of all these points and compares it to the original and produces a new transform which we can use. So if we can move these points around with the field, then we can move the object around with the field and we can do some fun stuff. Okay. We don't really need the group at the moment because we're going to do this on all the points. So we need to put something in here, and the thing we're going to put in here is a solver. So we're going to make our own little mini dynamic system for this with this solver, and we'll delete the transform. So solver does the same thing on an object over and over again, depending on what data you put into it. I'll dive in here. So for instance, if I make a transform and put that on there, and I don't know, maybe put the scale as 1.05, then every frame it'll do the same thing to it, so it gets bigger by 1.05 every frame. Or we could put minus 0.1 in there, so it gets bigger and moves down at the same time, like that. But we're going to use a wrangle, not a transform. So let's put a point wrangle in there, because points is all we've got. So similar sort of thing we could do with the wrangle, which is at p plus equals comma minus 0.01 comma 0. same sort of thing. But we want to use acceleration, velocity and position. We'll set up a quick dynamics solver using those parameters. So first of all, we need gravity equals minus 9.81. That's pretty standard value for gravity. So that will be acceleration for the points when they're out of the water, just be falling in gravity. So we'll call our acceleration attribute accel, so at it's vector v at accel equals, if you've got a variable or something inside the vector, then you're going to need to use the set command here. So set and then it's brackets 0, g, 0. We'll check that with the geometry spreadsheet. And there's our accel minus 9.81. And then we have v at v. So the acceleration updates the velocity every frame. So now our value of velocity, we can see here that goes crazy. That's because acceleration is making it bigger every time. And finally, position is updated every frame also. We're running into a problem here of calibration, I think. So that's falling rather fast. There we go. And we can check how fast that's falling by, if we just drop down a box and make that a rigid object, rigid body hero object. We can see that our pig drops off a good bit faster. This rigid object has the default value in Houdini, so we know that's right. So something wrong with our solver. And what's wrong with it is we are making it update. That's 9.81 is our acceleration there. That's per second, and we've got 24 frames in a second, so we've got to update. We're updating 24 times in a second with the second value here, and we need to divide that by the number of frames per second, which is $FPS, and the same on the velocity and position. There we go, and you can see the box and the head drop at roughly the same rate. Next thing is to connect the volume here, the SDF from here into second input, and then we can use that to determine whether or not a point is above the water and subject to just acceleration, or below the water and subject to both acceleration and buoyancy. So we connected that to input 2, and now we need an attribute from volume. attribute name is surface. Volume is surface. Let's just check that it came in okay. Surface, yep, there we go. And its attribute size is 1 because it's just a float. So now let's visualize that attribute. That's good. As it goes down, it updates with the SDF, and we have different values. So those values will be from -1 to +2. Well, the ones that are positive values are above the water, and the ones that are negative values are below the water. So we need a conditional statement. So let's put one in there. If at surface is greater than 0, then we do one thing. Otherwise, we do another thing. And the thing we want to do is, when it's above the water, is that. Good, still works. Clearly we need something to go in here as well, which represents the motion of the particles under the water. But for now, I'm just going to put this in as a placeholder and get the rest of it working, and we can work out exactly what's going in here with physics. So as a placeholder, I'm just going to put that in there, but I'm going to go G star minus 0.5. So that's a force equivalent to half of gravity and pushing up instead of down. Okay, so let's play that again. Perfect. Now you can see it goes weird, which is what I'm after, because we're missing a step. But, you know, that's fun too. So the step we're missing is we've got to force it back into its shape every frame. So a few particles have moved, a few points have moved, and that gives us our overall movement, but we need to do the extract transform trick again to get the actual movement. So drop down extract transform there, and wire that in. Oops. That goes in there, that goes in there, and then a copy to points again, and that goes to there. Still not quite there, is it? The reason it's not quite there is because for this to work, we need velocity to persist from one frame to the next. Now before, it came back in through previous frame, but now it gets wiped out in this stage. See? When we convert it from points into a single point, like that, which we then use to copy to points, we lose the velocity information that needs to pass through. So it's easily fixed. Just use an attribute transfer just to copy that back on, and attribute transfer on points, and just V. So there we go. There's our So what do we get now? Okay, that's starting to get interesting. It's obviously not quite there yet because floating objects don't do that, but it's getting interesting. Clearly we have some way to go yet. We need a proper term in here. Okay, and the reason, I mean, that's just a force on every particle that pushes back a little bit. But if we have a proper term that takes into account density, then we can then produce an object that has different density in different places. For instance, if you were to glue a bolt onto a beach ball, you know that the bolt would always move down to the bottom when you chucked it in the water. So we can replicate that behavior. So we need a decent density term, but also it's coming right out of the water every time it bounces, which is not realistic, and the reason for that is that we need a viscosity element. So when the object's under the water, it also, as well as being affected by buoyancy, it is affected by viscosity. So we need to work out a viscosity term, and then the last thing we need to do is to work out the effect of the currents in the water going side to side. So we've dealt with the up and down motion, but we need to deal with the side to side motion using the velocity field that the Ocean Evaluate can output. We will fix these things in part 2. Please like and subscribe if you've enjoyed this video.